In the previous lecture, we had talked about the Rayleigh method, which was one of the ways of getting an approximate solution to the boundary value problem of interest. What we had done is we had taken a simple problem of a bar subjected to an end load P of size 10 and a uniformly distributed body force Fx of intensity x. At x equal to 0, we had fixed the bar, that is, this was a fixed boundary condition, and at x equal to 1, we had the P applied, that is, the force was applied at x equal to 1. For this problem, we wanted to get an approximate solution using the Rayleigh method. So how did we proceed? We took the so-called functional, which was nothing but the total potential energy for the structure, which was given as half integral 0 to 1 u prime squared dx minus p u evaluated at 1. Remember, here we had taken the material to be such that Ea is equal to 1. So minimization of this pi u, that is the first variation of pi, gave us integral 0 to 1 u prime variation of u prime dx minus p variation of u at x equal to 1 was equal to 0. Then we went ahead and used a series representation for u. We said that we will take a so-called two-term solution. u2x was equal to u1x plus u2x squared. This is a two-term solution that we took. Why did we take it of this type? Because we wanted this u2x also to satisfy the specified geometric conditions at the point x equal to 0. And as you see that here the x and x squared vanishes at the point x equal to 0. In order to find the coefficients u1 and u2 of this series solution, we went back to this variational form that we have written here, and in that we took delta u was equal to delta u1 into x plus delta u2 into x squared. So when we substitute that, now this delta u is something that is under our control. It is the variation or the virtual displacement that we are talking about. So I can choose first, since it's under our control. So we'll set delta u2 is equal to 0, delta u1 is equal to 1, and we'll get one equation. Then in the second one, we are going to set delta u1 is equal to 0, delta u2 equal to 1, and we'll get the second equation. This we have done in the previous lecture, so I'm not going to go over it again. After doing all this, we will get the solution to the problem that we have defined. So let me again write it. We'll get integral 0 to 1 u2 prime into x prime dx is equal to integral 0 to 1 x into x dx minus plus 10 into x evaluated at 1. This is the first equation we get, and the second equation we have is u2 prime x squared prime dx is equal to integral 0 to 1 x into x squared dx plus 10 into x squared evaluated at 1. So out of these two equations, now substituting for the representation for u2 prime, I'll get the solution to this problem. And what we got in the last lecture was u2x was 10.5833x minus 0.25 x squared. This solution that we obtained for u2x is very close to the exact solution to the problem, which was equal to 10.5 x minus 1/6 x cubed. So when we plot this, we'll find that this u2x is quite close, and for engineering accuracies that we desire, this is a good enough solution. If we went ahead and took the 3-term solution instead of u2x, if we took u3x, this was equal to u1 into x plus u2 into x squared plus u3 into x cubed, then we'll see that by going through the whole procedure, we'll get the exact solution back. So what the Rayleigh-Ritz method has done for us is that by taking this appropriate functions, which we had called as our basis functions, which are polynomial functions, x, x squared and x cubed, we have been able to recover the exact solution for this particular problem exactly using a 3-term solution. Is this picture as rosy as what we have said using this example? The answer is no. So let us look at the second problem that we had posed. So here again we had said that P is 10 units. At this point, I am going to apply a concentrated load of size 20 units. This is the point x equal to half. This is the point x equal to 1. This is x equal to 0. If I go ahead and write the total potential energy for this problem, it will be half integral of 0 to 1 u prime squared dx plus 20 u evaluated at x equal to half, sorry, not plus but minus 10 u evaluated at x equal to 1. So if I take the first variation of this pi, this will be equal to integral 0 to 1 u prime variation of u prime dx minus 20 variation of u at x equal to half minus 10 variation of u evaluated at x equal to 1. This whole thing is equal to 0. Again, if I take a 2-term solution as an approximation to the u of the problem, so u2x again, as we had done for the previous case, is equal to u1 into x plus u2 x squared. So again we go through the same steps as we had followed for the previous problem, and we can obtain the coefficients u1 and u2 of the exact solution of the approximate solution that we have obtained. For this problem, let me first write the exact solution. Exact solution of this problem is equal to, if you look at it, it is 30x for this part and 10x plus 10 for this part. So if you look at the exact solution is a piecewise linear. That is, it is linear in the part 0 to half and linear in the part half to 1 with the slopes different in the two parts. Now if I look at the two-term solution for this problem, let's see what it is. 35x minus 15x squared. Look at this solution. It is certainly not a piecewise linear. It is a quadratic polynomial. If I look at the value of this solution at the point x equal to 1, so u2 at the point 1, this is equal to 20. If I look at the value of the exact solution at the point x equal to 1, it is also 20. So things look to be quite good. The answer is no. Look at the derivative of this solution. u2 prime evaluated at x equal to 1 will be equal to 35 minus 30x evaluated at 1, which is equal to 5. What is the derivative of the exact solution? The derivative of the exact solution is 10. So we have an error of 5 in the derivative of the approximate two-term solution that we have obtained, and this error is 100%. Now in most of our computations, we are not interested in the value of the solution. We are mostly interested in the derivatives of the solution because we want to obtain the strain as well as the stress information out of this computation. So you see that this is a disaster as far as the numerical solution is concerned. Now again, if I go back to the point half and obtain the u2 prime at x equal to half. So this will be equal to, as we have obtained, it will be 35 minus 30x evaluated at half. Okay, so this will be 35 minus 15, which is equal to 20. This is one number. What about the derivative of the exact solution? So exact solution, if I look at it, is equal to the derivative of it, 30 for x is equal to half minus epsilon. That is, I am very close to x, but coming at it from the left hand side, and it is equal to 10 at the point x is equal to half plus epsilon. That is, I am coming to the point x equal to half from the right hand side. That is, this is my point x equal to half. Derivative in this region is 30, derivative in this region is 10. And what has the approximate solution given me? It has given me the average value of these two derivatives. Again, the numerical solution is not able to capture this jump in the derivative, which is inherent in the approximation that we have made. Now, are these problems of interest to us, or these are simply artifacts that are created to show that the Rayleigh-Ritz method does not function? Unfortunately, most of the engineering problems that we are interested in do have this kind of a feature. For example, I may have a very general problem of a bar with multiple concentrated loads coming due to fixtures which may be attached to this bar. So I may have a concentrated load F1 here, F2 here, F3 here. Similarly, I may have another problem where I will have a bar, I can give it an end load P, no problem, but the bar is now made of different materials. That is, there is one material here, another material here, another here, another here. So I may have EA1 here, EA2 here, EA3 here, EA4 here. Okay, this may be a problem that is of interest to us. In all these cases, that is, in both these cases, the solution, if I look at the exact solution, it does something like this. That is, the solution is so-called piecewise smooth and continuous. This is what the engineering problems have as a feature, because continuity is required, otherwise my specimen is going to break. So in most such problems where I have dissimilar materials or point loads applied at certain locations, the solution is going to behave like this. Now I could have also put some distributed load, no problem, on the structure. That is not going to change the nature of the solution. That is, at these points of transition of the material or the points where the concentrated loads are applied, we will have a change in slope that is inherent. Okay. So these are the solutions that we are interested in, and we have seen that our so-called two-term solution that we have obtained for the model problem of interest, that the second model problem that we had put. So the two-term solution does something like this. This is the exact solution, and if I look at my approximation, the approximation does something like this. The question is, what if I took a three-term solution? Three-term solution gives exactly the two-term solution back. That is, the cubic part of the solution, if you go ahead and solve it, is 0. So taking higher and higher terms really does not solve the problem. So how do we solve this problem? So for this, very simple thing that we can do is, we can change the definition of these basis functions that we are using to represent the solution. If you remember that this we had written as I is equal to 1 to n, in this case ui phi I of x. Till now we had taken these as polynomials. What if I go ahead and do the following thing for the model problem 2 that we have taken? So this is x equal to 0, x equal to half, x equal to 1. So what should I do? I do the following, that now I construct these functions phi I in such a way that this is my so-called phi 0 of x, this is my so-called phi 1 of x, and then this is my phi 2 of x. So what have I done? I have put this intermediate point at x equal to half in my domain. This is the point where I have applied my concentrated load. Now these phi's I am going to define as so-called piecewise linear functions. These are piecewise linear and continuous. And if you look at these points, these functions have a very special property. That is, this phi 0 at the point x equal to 0 is equal to 1. Phi 1 at the point x equal to half is equal to 1. Phi 2 at the point x equal to 1 is equal to 1. And if you look at these pictures, that these functions at all other points, they go to 0. That is, if I call this as point x0, this as x1 and x2, then phi 0 is 1 at the point x0, 0 at the point x1 and x2. Phi 1 is 1 at the point x1, 0 at the point x0 and x2. And phi 2 is 1 at the point x2, 0 at the point x0 and x1. This is my construction of these functions which are going to be used to represent the series solution. Let us see if this is going to help. So, if I have to do this, now use these functions, what are these functions? If I go to the representation, so if I do now u, I'll call it, still I'll call it u2x, you'll see the reason why. This is equal to u naught phi naught of x plus u1 phi 1 of x plus u2 phi 2 of x. Now, what do we want our functions to do? Because we are still in the regime of the Rayleigh-Ritz method. We want this u2 at the point x equal to 0 to be equal to 0. That is my solution. My series solution has to satisfy the specified geometric boundary conditions. So, if this is equal to 0, at the point x equal to 0, what do I know? u1 is equal to 0, phi 1 is equal to 0, phi 2 is equal to 0, phi naught is equal to 1. So, this becomes equal to u naught. So, I can knock off the u naught from here. So, I am left with two terms, that is why I wrote it as a two-term solution. Now, I have to obtain these coefficients u1 and u2. So, how do I obtain the coefficients? Again, I go back to my definition of the total potential energy of the structure, and we again look for the values of this u1 and u2 which minimize the total potential energy. That is, I am looking for the first variation of pi, which here is a function of u2 is equal to 0. So, what do we get? So, we will get integral, let us take the second problem only, 0 to 1 u2 prime phi 1 prime dx is equal to f phi 1 evaluated at the point x equal to half plus p phi 1 evaluated at the point x equal to 1. Similarly, I will get for the second one u2 prime phi 2 prime dx, this is equal to f phi 2 evaluated at the point x equal to half plus p phi 2 evaluated at the point x equal to 1. I have simply replaced, instead of the polynomials, a generic definitions of these phi's. So, these are the two equations that we will get. Now, I will substitute u2 as u1 phi 1 plus u2 phi 2. So, if I substitute this thing, then what are the equations I am going to get? I am going to get u1 integral 0 to 1 phi 1 prime squared dx plus u2 integral 0 to 1 phi 1 prime phi 2 prime dx, this is equal to f phi 1 evaluated at the point half plus p phi 1 evaluated at the point 1. This is the first equation. Similarly, I will get for the second equation integral 0 to 1 u1 into phi 1 prime phi 2 prime dx plus u2 integral 0 to 1 phi 2 prime squared dx, this is equal to f phi 2 evaluated at x equal to half plus p phi 2 evaluated at x equal to 1. So, you see that these are essentially two algebraic equations in terms of simultaneous equations in terms of the unknown coefficients u1 and u2. Okay. So let us now define these functions phi 1. If you look at this function phi 1, what does it do? So it is linear in this part from 0 to half, linear in this part from half to 1, and it is continuous at the point x equal to half. So it's very easy to define this function phi 1x. This is equal to, if it is linear here in this region and it has a value 1 at the point x equal to half, then if I make it 2x, then you see that it satisfies this condition, that at x equal to half it is 1, x equal to 0 it is 0. Now in this region it is equal to 1 here, 0 at the point x equal to 1. So this one will be, in this region if I want to define it, it will be 2 into one minus x. Look at it, at x equal to half, this number is equal to half, 2 into half is 1, at x equal to 1, this is 0. So this is a linear, this is also linear, so this phi 1 is piecewise linear and it is given by this. Similarly, if I want to define phi 2 of x, so phi 2 of x, if you remember, it is like this. So what is the value of phi 2 of x? And this is half is in the region 0 to half. If you see this line, it is 0 in this region. So it is this. In this region, it is a linear and it takes a value of 1 at the point x equal to 1 and it is 0 at the point x equal to half. So if I make it as this, 2x minus 1 in the region half less than equal to x less than equal to 1. So you see that at the point x equal to half, this expression is 0, at the point x equal to 1, this expression is 1. So this is our representation of phi 2x. Now these two representations we have to plug back in our equations that we have written, the two simultaneous equations, evaluate these integrals and then solve the corresponding problem. So I will do the first equation. So if you look at this, so you have the first equation is u1 into, if I write it, integral of 0 to half phi 1 prime, which is dx plus integral half to 1 dx plus u2 into integral 0 to half phi 1 prime phi 2 prime dx plus integral half to 1 integral phi 1 prime phi 2 prime dx. This will be equal to, f is equal to 20 for us, into phi 1 evaluated at the point x equal to half. So phi 1 at the point x equal to half is equal to 1 plus p is equal to 10, phi 1 evaluated at the point x equal to 1, which is 0. So now let us look at these terms that we have obtained. So for us, the phi 1 is equal to what? in the region 0 to half. In the region 0 to half, phi 1 is equal to 2. So I will get phi 1 prime is equal to 2. So 2 squared is 4. Integrate from 0 to half, so it will be 4x. So it is going to be 4 into half, which is 2. Plus, in the region half to 1, what is phi 1? We obtained that phi 1 was equal to 2 into 1 minus x. So phi 1 prime is equal to minus 2. Minus 2 squared is 4. 4 in x is equal to 4 into half, which is again 2. Plus, I will have the u2 part. 0 to half, phi 1 prime is equal to 2. What is phi 2 prime? Since phi 2 is equal to 0 in the region 0 to half, phi 2 prime is also equal to 0. So this is equal to 0. Plus, in the region half to 1. In this region, both phi 1 prime and phi 2 prime are non-zero. So what is phi 1 prime in the region half to 1? It is minus 2. Phi 2 prime, what is it equal to? It is plus 2. So it will be equal to what we have, minus 2 into plus 2 into half. This is equal to 20. So I will get this equation will become, let me now highlight this equation. So it will become 4u1 minus 2u2 is equal to 20. This is my, I will call it equation A. Similarly, if I went ahead and did the exercise for the second equation, I will end up getting for the second equation minus 2u1 plus 2u2 is equal to f into phi 2 evaluated at the point x equal to half, but phi 2 at the point x equal to half is 0, plus p into phi 2 evaluated at the point x equal to 1. So it is phi 2 at the point x equal to 1 is 1. This is my equation P. So if I write it in matrix form, what will I get? I will get 4 minus 2 minus 2 2. This into u1 u2 is equal to 20 and 10. So I have to solve this matrix problem. So it's very easy to invert this matrix. So I will get, after inversion, u1 u2 is equal to this is equal to, so half into 20 is 10 plus half into 10 is 5, so this will be equal to 15. Here half into 20 is 10 plus 1 into 10 is 10. This will become 20. So I have been able to solve this matrix problem to obtain this two-term solution coefficients u1 and u2. So now my solution u2 of x is equal to 15 phi 1 of x plus 20 phi 2 of x. What was our exact solution? If you remember, u exact of x was equal to 30x in the region 0 is less than equal to x is less than equal to half, and 10 plus 10x in the region half less than equal to x is less than equal to 1. So now if I go to this point x equal to half, at the point x equal to half, u exact is equal to 15, at the point x equal to half, what is u2 equal to? At the point x equal to half, you will see that phi 1 is equal to 1, phi 2 is equal to 0. So u2 is equal to 15, which is equal to u exact at the point half. Similarly, if I go to the point x equal to 1, at the point x equal to 1, u2 at the point 1 is equal to 15 phi 1. Phi 1 at the point x equal to 1 is 0, phi 2 at the point x equal to 1 is 1. So this will be equal to 20. And from this expression, if you see, it becomes equal to u exact at the point x equal to 1. So at both these points, x equal to half and x equal to 1, these two solutions are the same. In between, they are both piecewise linears. So what do we know? That to define a linear, we need 2 points. At both points, these two solutions are the same. So my u2 of x is identically equal to u exact. That is, using these functions phi I that we have redefined, that is this piecewise polynomial functions, piecewise linear functions, I have been able to capture the exact solution to the boundary value problem that we had been interested in. So is this a solution? The answer is yes. This is one way we can obtain solutions to the problems which have concentrated loads or material interfaces. So let us see what is so nice about these functions phi I x that allows us to get the exact solution to the second problem that we had posed. See, there are certain properties that these functions have to satisfy. This is something that we have to keep in our head. Whenever we want to construct such piecewise polynomial functions, we have to ensure that certain basic properties are satisfied by these functions. One is that, well, they are piecewise polynomials. Then they are continuous. That is, in the whole domain, these functions are continuous. Secondly, in this problem, what have we done? We have taken these functions such that the value is continuous, derivative is not continuous. So at the interface of the two pieces that we have taken, this kind of functions which do not satisfy continuity of derivatives at certain points are called C0 functions. Fourthly, what these functions have to do is that they have to form something called a complete set. What does this completeness mean? So if I look at what we had done earlier, x naught is equal to 0. I'll just take only one part of the domain. In this, I had drawn this function phi 0 and this function phi 1. What completeness means is that the linear combination of these functions phi 0 and phi 1 should be able to represent any polynomial that we take such that this polynomial is linear. That is, I should be able to find these unique constants a0 and a1 such that I should be able to represent the polynomial b1 plus b2x, the linear polynomial in this region, exactly using the linear combination. This is called completeness. If you look at this particular example and let's say we knock off b2, that is, I look at a constant, then I should be able to represent a constant also exactly in terms of a linear combinations of this phi 0 and phi 1. How will I do it? Very simple case. is that if you look at this phi naught and phi 1, sum them up, the sum of these two functions is equal to 1 at all points in the region x equal to 0 to x equal to half. So very simple situation we have is that a naught phi naught plus a1 phi 1 is equal to b1. Trivially we will get that a naught is equal to b1, a1 is equal to b1. So I am able to represent even a constant in this region. Another very important property that these functions have to have, which we have outlined earlier, is linear independence. What does the linear independence mean? That if I take any combination of these functions, so I will do a naught phi naught plus a1 phi 1 plus a2 phi 2, and I set it equal to 0 everywhere in the interval 0 to 1, because these functions are defined in the interval 0 to 1. So that's where I am going to concentrate. So in the interval, this I want to be equal to 0 for all x's x lying between the points 0 to 1. So what does the linear independence requirement tell us? That if this is so, then all these coefficients a naught, a1, a2 should trivially come out to be equal to 0. Is it so for our functions that we have taken? Since this has to vanish at all points in the interval 0 to 1, let us take the three specific points x0, x1 and x2 that we have taken. They have to vanish there also. So x0 is equal to 0, x1 is equal to half, x2 is equal to 1. So what happens at the point x0? At the point x0, if I look at this expression, phi 1 is equal to 0, phi 2 is equal to 0. So at the point x0, so at x equal to x0, this expression becomes a0. This is equal to 0. Similarly, at the point x is equal to x1, what happens? My phi naught is equal to 0, phi 2 is equal to 0, phi 1 is equal to 1. So this expression becomes a1 is equal to 0. At x is equal to x2, again by the same token, phi 2 is equal to 1, phi 1 and phi naught are 0. So my a2 becomes equal to 0. This is exactly what we needed for linear independence. So these functions phi i's that we have constructed are indeed linearly independent, piecewise linears, complete, continuous, and we say that they belong to C0. Now the question is that what kind of a job do these functions do in approximating the exact solution of the first model problem that we had taken? Because the second one, yes, it did a good job. What about the first one? So let's go back to that model problem. Here we have p is equal to 10. This is fx is equal to x. So for this model problem, how do we go about again finding a solution? Same process that we had done for the problem with these concentrated loads. The only difference that we'll have is that in this case I will get integral of 0 to 1 u prime delta u prime dx is equal to integral 0 to 1 fx delta u dx plus p delta u evaluated at x equal to 1. And if you remember that our delta u is again equal to, if I take a two term solution, delta u1 phi 1 plus delta u2 phi 2. Plug everything into this expression and taking first delta u is equal to phi 1, then taking delta u is equal to phi 2, I get the two equations for the two term solution. it should be obvious to you that the right hand side of this equation remains the same as what we had obtained for the case with the concentrated loads. Why? Because the right hand side, sorry, the left hand side of the equation remains the same as for the concentrated load, simply because the left hand side remains unchanged for both the problems. Only this right hand side, which corresponds to the load, the effect of the load, externally applied forces, that is going to change. So what we can do is, we can again pose the problem like this. I am simply going through the steps. So it is integral 0 to 1 x phi 1 dx plus 0, because phi 1 at the point x equal to 1 is equal to 0, and this one will be, the second part will be x phi 2 dx plus p. Why? Because phi 2 at the point x equal to 1 is equal to 1. So the load vector that we obtain is different from the problem with the concentrated loads that we had taken, but the so-called stiffness matrix that we had defined much earlier remains unchanged. Okay, so if I go and evaluate the load vector, I will get again solve for u1 and u2. So your u1 and u2 becomes equal to 251 by 48 and 31 by 3. Now if you compare with the exact solution of this problem, you will see a very curious observation, that the u exact at the point x equal to half is equal to 251 by 48, which is equal to u1, which is equal to the two-term solution evaluated at the point x equal to half. Similarly, u exact at the point x equal to 1 will be equal to 31 by 3, which is equal to u2, which is equal to the two-term solution evaluated at x equal to 1. So you see that the exact solution matches the two-term solution that we have taken using these special phi's that we have defined at the points x equal to half and x equal to 1, which we have called as also points x1 and x2. So if I plot the function, here is x, here is u, you will see that your u exact will do something like this, and this is half, this is 1. Your two-term solution will do something like this. Now, what if I want to improve the accuracy of the solution? If you see the solution, certainly in between here it is not great. That is, the gap between the two-term solution and the exact solution is quite high. What if I want to reduce the gap? So for that, what do? I will introduce more points in the domain. So earlier I had these 3 points, x0, x1, x2. I am going to add another 2 points such that they divide. I will call it x2. This point is x3. this point is x4. So what they do, they divide each of these earlier pieces into half. Okay. Now I am going to define these functions phi i's over these pieces. So this will be my phi naught, this will be phi 1, this will be phi 2, this will be phi 3, this will be phi 4. So phi naught, phi 1, phi 2, phi 3 and phi 4. Now if I go ahead and again represent the so-called 4-term solution in terms of u1 phi 1 plus u2 phi 2 plus u3 phi 3 plus u4 phi 4 and solve the problem, what I will see is the following, that I will get now the new solution will look like this. That is, the 4-term solution is closer to the exact solution as compared to the 2-term solution. So in principle, what I can do is I can keep on refining this subdivision. That is, I keep on adding these points which divide the previous subinterval into half, and I can keep on getting, hopefully, closer and closer to the exact solution. So this is something that we call convergence. And in principle, at least it looks like that this kind of a series solution does converge to the exact solution if I take more and more terms in the series. That is, I take these finer and finer distribution of points with respect to which I am defining these functions. Now, these points that we have given, they are given a name. They are called nodes. And the region between two consecutive nodes, the interval, the subinterval, is called an element. These nodes and these elements together constitute a partition of the initial domain of interest into smaller pieces. So what do these nodes do? They define the extremities of the elements. For example, if I am looking at element 2 here, this element 2 will have as its extremity the point, sorry, this is not element 2, this is element 2, will have as its extremity points x1 and x3. So element 2 will have these 2 points as its extremity, and so on. So what we have done is we have laid the foundation of a method by which we can define better and better approximations to our boundary value problem of interest using certain principles of partitioning of the domain into smaller and smaller elements, defining these extremities of the elements which are called the nodes. This together, this whole concept of breaking the domain into smaller pieces or subdomains is what we call the finite element method. And you see these phi's that we have defined are only non-zero in a small neighborhood of the point with respect to which they are defined. That is, in the two neighboring elements which are joined at this point xi, this function phi I is non-zero, elsewhere it is 0. So these are all so-called basis functions which have local support. That is, they are non-zero in only a small part of the domain, 0 everywhere else. In terms of these basis functions, we can construct a series solution to the problem of interest, and hopefully the series solution, if I take finer and finer partitioning of the domain, will converge to the exact solution. The whole process of partitioning of the domain, that is assigning these nodes, is called meshing. And the process by which we are converging, that is by adding more and more nodes, This kind of a process is called H version of the finite element method. So what we are going to concentrate is in the so-called H version of the finite element method, and we'll see whether we can guarantee convergence of the approximate solution to the exact solution. And we see that this kind of a basis is able to capture the solutions to problems with continuously distributed loads or concentrated loads or material interfaces, provided we put the so-called nodes at the interfaces. That is, if I have a domain like this, let me take a very pathological example. That is, here I have some material, here I have a concentrated load. Then the partitioning that I do, that is, these nodes that I put, will be here, it can be here, it has to be here. One node has to be at the interface of the two materials. This is one material, this is another material. Another node I can put here, and another node has to be at the point where the concentrated load is applied, and so on. This way I can define the partitioning of the domain, and based on the partitioning of the domain, since these functions phi i's are defined with respect to these nodes, I can define what are these functions phi I, so on. Okay, and go ahead and construct my approximate solution to the problem of interest. So in this lecture, what we have seen is that the Rayleigh method does a good job with polynomial approximating functions for domains with one type of material, with loading which is nice and continuous. Then the Rayleigh method does a good job. If I have dissimilar materials or concentrated loads, then the Rayleigh method using polynomial approximation fails. And that was a motivation for introduction of these piecewise polynomial functions, which constitute the basis of the finite element method that we are going to develop in the next lecture. Using the simple one-dimensional model problem, we will go ahead and give the detailed formulation of how to construct this matrix problem in order to determine the unknown coefficients. We will solve that problem and see how the solution looks like, what is the accuracy of the solution, and when the solution will do certain nice things and when will the solution fail. So that will be a starting point of the finite element method. Okay.